Good afternoon. My name is Blanca Beato Arribas and I am the microclimate team leader of Bistria Test. This webinar on indoor air quality is part of a series on indoor environmental quality, and we will put all the webinars on the Bistria webpage if you would like to have access to them. So today we're going to start with a brief introduction to air quality, how the main contaminants are classified, how to measure the air quality, and what is the role of ventilation and maintenance. So let's start with a definition for air quality. Good indoor air quality is defined as air with no non-contaminants at harmful concentrations. This means that the air that we breathe is not exactly contaminant-free, and what we're going to see in this webinar is what are harmful concentrations of contaminants. In order to have good indoor air quality, we have to have a series of requirements, which are to have low external pollution concentrations, low pollutant emission rates from internal sources, including materials, and to have a good ventilation to dilute and remove the pollutants, because sometimes indoor air quality is actually 8 to 10 times worse than the air outside. So the main contaminants of air can be classified in 5 groups, which are particles, gases, odors, volatile organic compounds, and biological contaminants such as mold or bacteria. Well, let's start with particles. Particle matter is composed of small particles that are suspended in the air and settle to the ground slowly, and they can be classified in smoke, fine dust, fumes, or mist. The sources of particles can be anthropogenic, for example, from oil and gas extraction or traffic, but they can also be natural, for example, during sandstorms or during the eruption of a volcano. What happens with these particles is that they can penetrate our respiratory system, and the smaller they are, the deeper into the respiratory system they can go, and they can cause a series of different health issues. So to give you an idea of how small particles can be, what you can see here is a drawing of a hair, which is visible to the human eye, next to a fine beach sand. And what you can see in blue, which is not visible to the human eye, are 2 common particles, which are PM10 and PM25, which are particles that are smaller than 10 microns and particles that are smaller than 2.5 microns. And the reason why we are talking about PM2.5 and PM10 is because the World Health Organization, the Health and Safety Executive, and the governments of many countries are concerned about these two because of their effect on health, and they are trying to limit it. So here you can see the limits for PM2.5 and PM10. This normally refers to air outside, but it has quite an effect on health, and they can actually travel inside. If you want to have more information about particles, a few months ago, Bistria and TSI presented a webinar on aerosol particles. So you can watch it at any time, as it's free on the Bistria webpage. The next contaminants that I'm going to talk about are gases. So there are many gaseous pollutants, and their effect on health varies depending on the type of pollutant and on the concentration that we are exposed to. So we're going to talk about a few gases today, which are of particular concern to health. We cannot talk about all of the gases, but we've selected a few. So we're going to talk about sulfur dioxide, radon, nitrogen oxides and ozone, carbon dioxide, and carbon monoxide. So to begin with, sulfur dioxide is a colorless, highly reactive gas that has a very pungent smell. and it can be found naturally in fossil fuels. So when these fossil fuels are burned, or when we have a volcanic eruption as well, SO2 can be released, and this gas is one of the main contributors to acid rain. And the effect on health can be very damaging, even if we're exposed to it for a short period of time. The effects on health can go from having a burning sensation due to short-term exposure in our respiratory system, but long-time exposure can aggravate asthma, can aggravate existing heart diseases, and can lead to changes in lung function. The next contaminants that I'm going to talk about are nitrogen oxides. As many gaseous contaminants, they are formed due to combustion of fossil fuels, and especially we have heard about the high levels of contaminants in cities because of traffic congestion, and probably we have also heard about the reduction of the levels of nitrogen dioxides during lockdown. So the short-term effects on health, they can include respiratory problems, but the long-term effects to exposure to nitrous oxides can create heart conditions and lung damage. And on top of everything, when nitrogen oxides combine with volatile organic compounds, they can form ground-level ozone, which is also another air contaminant. The next contaminant is radon. Radon is produced by radioactive decay of radium, and it's found in rocks. So when the dust gets into our lungs, it emits radiation that can damage our lungs. So on the right-hand side of the picture, you can see a drawing from Radon UK, which highlights in darker colors the areas where radon occurs naturally in England and in Wales, is this picture. So for those of you who have a house there, there are some things that you can do to avoid having radon in your home. For example, you could have a radon sump, which consists on extracting the air possibly contaminated with radon from the lower area of the house. You could have positive ventilation in your house. So if you have positive ventilation, the air is going to flow from the house into this area here and not the other way around. And you could have natural underfloor ventilation or active underfloor ventilation. Right. The next gas in our list is carbon monoxide, or CO. Carbon monoxide is a very dangerous gas because it's colorless and odorless, and it's lethal at very low concentration. So when a person breathes in carbon monoxide, it binds with hemoglobin and it inhibits the blood's ability to carry oxygen or to get rid of CO2. So eventually a person would go unconscious and would die, and sometimes this happens during the night when people are asleep due to poor combustion of any fossil fuel appliances, and this is why this gas is called the silent killer. And the last gas that I'm going to talk about is carbon dioxide, CO2. CO2 is not lethal at low concentrations. Actually, you have to have a very high concentration of CO2 to be killed, unlike carbon monoxide. The advantage of CO2 is that it is a gas that is very easy to measure, and it can give us a very good idea of the ventilation in the space. So we have a formula here that can help us calculate the concentration of contaminants in space based on the knowledge of the emission rate of this contaminant, in this case CO2, and based on the knowledge of the ventilation system and the space volume. So for example, if we were in a classroom that is empty and then everybody comes in for the classroom, and as we breathe CO2, the levels of CO2, they begin to rise. And if we have the same amount of ventilation and the same amount of people in the room, eventually the CO2 will achieve a steady state. It doesn't go on rising indefinitely. So steady state level depends on several things. It depends on the number of occupants in the space, it depends on the volume of the space, and it depends on the ventilation rate. So for example, if we compare the red line with the blue line, the red line shows a space that has a higher ventilation rate with the same amount of people and the same space as the blue line, but it has a lower contaminant concentration because it has a higher ventilation rate. And the difference between, for example, the blue and the green line is that the green line shows a room that is higher, that is a larger room, and therefore achieving steady state takes a longer time. So this is an example, a more realistic example of what happens if people come in and out of a room. That could be a classroom. So the levels of CO2 vary with whether people go in the room, come out of the room, go in the room, and finally leave for the night. And here we can see another use of measuring CO2 in the space, which is that using this formula, we can calculate the effective air change rate that a room has just by analyzing the decay curve if everybody lives at approximately the same time. And finally here, we can see a table of the effects that carbon dioxide has in our health. So as I mentioned before, you have to have a really high level of CO2 to actually kill you, and the health and safety limit is actually 5,000 ppm. The issue with CO2 is that when the concentration in space is higher than 1,000, so for example 2,000 ppm, it's below the legal limit. However, you begin to have concentration problems. It begins to feel stuffy, and this is why normally in the industry we use 1,000 ppm as the limit to establish whether the ventilation in a space is good or bad, and not 5,000. So we have seen a few gases and their effect on health, and now we're going to move to the next type of contaminants indoors, which are VOCs. So VOCs, or volatile organic compounds, are carbon-based materials that can easily evaporate at room temperature. And generally they come from building materials, from carpets, painting, furniture, or cleaning products. Sometimes they come from personal care products such as perfumes or nail polish. And basically, if you have a new car, or if you enter a newly painted room, is that a smell? Probably you're exposing yourself to VOCs. So their effect on health is varied, because there is a very large number of VOCs, and some are not harmful to your health and some are very damaging to your health. And in this table you have an example of a few VOCs and their exposure limits, which is something that I'm going to talk about in a minute in this presentation. And if you want more information about the types of VOCs, I suggest that you go to the Health and Safety Executive webpage, because you can find the limits in there for every type of contaminant. Right. The next contaminant that we're going to talk about is odors. Odors and air quality are very closely linked to each other. So some contaminants can be quite smelly, others, like for example carbon monoxide, and the sources of smells can be, for example, cooking processes, sinks, waste drains, rubbish. And there is a way to quantify odor emissions. Professor Ole Fanger from the University of Denmark, he did a huge research on thermal comfort and also in odors. And he defined two new units to measure odors, which are the olf and the decibel. So the OLF is the rate at which a human emits air pollutants, but this human has to have had 0.7 baths, which I assume is equivalent to a shower. This person also has to be wearing deodorant, but not perfume, and has to be comfortable with the temperature. And there is a table for with different examples of OLFs. For example, an adult exercising would be 3 OLFs, and a low polluting building would be 0.1 OLFs per square meter. And Professor Fanger also defined what a decibel is. So a decibel is the perceived air quality of 1 OLF when the space is being ventilated by 10 liters a second. And Fanger also established a relationship between OLF and the predicted percentage of dissatisfied people in an environment. And finally, the last component that I'm going to talk about is mold or bacteriological contaminants. So molds produce spores that float in the air, and when they land on surfaces, if the surfaces are damp, they can grow. Their effect on health goes from sneezing to having red eyes to provoking asthma attacks. And some sources of indoor mold can be, for example, when we are washing or cooking or showering and there is not the right extraction in the room. So the key to mold control is to control the moisture. In this section, we're going to talk about how to measure indoor air quality. So what we're going to see is where to find the contaminants and where to find the limits that are hazardous to health. We're going to see what the threshold limit values are. We're going to see the conversion between milligrams per cubic meter and ppm, and we're going to see some of the instrumentation that can be used for measuring contaminants. So this list here is an example of where to find the contaminants and the exposure limits. The HSE, the Health and Safety Executive, lists the contaminants that are harmful to health and that we have to comply with at work. And it also lists their exposure limits. And other places where we can find this information are the World Health Organization or CDC or OSHA in America. So the exposure limits have three components. The first one is the time-weighted average, or TWA, which is the concentration of a contaminant averaged over a workday, which is normally 8 hours. Then we have the ceiling value, which is the concentration of a toxic substance, which should not be exceeded at any time. And finally, some contaminants are so dangerous to health that they have a short-time exposure limit, which is basically the same as the TWA, but for a concentration over 15 minutes. So in this example, we can see what we're seeing is the exposure to an imaginary contaminant that a worker can have during a day. And here you can see the average over the 8 hours of work. And what you can see here in red is the ceiling value. And if you see, even if the TWA was under the exposure limit, this situation would not be acceptable because for a period of time, this person was exposed to a higher concentration than the ceiling value, which should never happen. So not all contaminants are the same. For example, we have spoken before about carbon monoxide, how it's dangerous at very low concentrations, and carbon dioxide is not dangerous at low concentrations. And there you have another one, for example, benzene, which has a TWA of 1 ppm, because it's quite a dangerous chemical. So The exposure limits of some contaminants are actually given in micrograms per cubic meter of air, or milligrams per cubic meter of air, and sometimes they are given in parts per million. So there is a formula, this formula, that depends on the temperature, but it can help you to convert from one another in case you need to. So if you have the concentration of ppm, you have to multiply it by the molecular weight and divide it by the molar volume of an ideal gas at 20 degrees. So the molecular weight for each element can be found in the periodic table. And what we would have to do is multiply the number of atoms of each element, depending on the formula of the contaminant, by its molecular weight and add it all up. And finally, here you can see some instrumentation to measure particles, to measure gases, for example, CO, CO2, VOCs. Some of these instruments, they offer you also temperature and humidity. But what I'm trying to illustrate here is that most gases can be measured with PID instrumentation, photoionization instrumentation. Other contaminants, or as well, some contaminants, they can be measured using active sampling. For example, dust sampling on a worker during a day, or VOCs. So how this works is we have a sample media, which for dust could be a filter, for total VOCs or for formaldehyde. We have different samples that have different media inside of them, for example, charcoal. And we force air to go through this sample, and then we send the sample to a laboratory for analysis. And we can use it on a worker, so they can carry this the whole day during their work, or we can actually set it up in a room and measure the contaminants in the space. This is an example of how to measure for bacteria, mold, and fungi. There are two ways. So you can have active sampling, in which, again, we force air to go through the sample, and in this case, the sample will be an agar plate. Or we can have passive sampling, in which we just open the agar plate in a space for a period of time, and then we would close it. We will send the samples to the laboratory where they would be incubated, and then they would count the colony forming units, which are actually these dots that you can see there. And depending on the contaminant, depending on the mold and bacteria that you have, there are different limits to what people should be exposed to. And what you can see here is another example of active sampling, but using an underset sampler. So in an underset sampler, you would put an agar plate in each of these 6 levels, and the underset sampler forces air through the sample. And what lands on these different agar plates are bacteria of different sizes. So the underset sampler simulates the human respiratory tract. So in this next section, we are going to see what to do when we have poor air quality in space, and what the role of ventilation and building maintenance is. So the way to deal with most contaminants is actually through ventilation, and also to remove the sources of contaminants. The role of ventilation is to provide fresh air to the occupants of the space, to remove the pollutants, the odors, and the heat loads in that space, and also to regulate the humidity. Unfortunately, sometimes when we go on site, we find images of the ventilation system like this one. So if we want indoor air quality, we want to limit the entry of outdoor contaminants, such as radon or nitrogen dioxides or particles, by having good filtration, or the radon methods that we talked about before. But we also want to have a cleaned, maintained, and easy to access ventilation system. We also need to change the filters and then carry out regular cleaning of the vents, of the grills, of the roof or wall terminals, and of the ducts and filters. And finally, we also need to limit the contaminants from indoor sources, either by having, for example, local extract ventilation, by monitoring the air that comes from outside. And we want to have good ventilation. For example, in this slide here, we have a supply grill and an extract grill really close to each other. So we can assume that part of the fresh air is going to go directly into the extract and is not going to reach the occupants of the space. So if we would like to measure the air quality in a building and we would like to know where to start, we could follow these following 4 areas. So if the building is occupied during testing, we could measure for CO2. And if it's not, we can check the volume flow rates of the building. The next step would be, if the building is new or refurbished, we could measure for VOCs, because it's a contaminant that we will probably find. And the next step would be, if there are odor complaints, we can either look for contaminants that are quite smelly, or we could check the supply and extract grill positions, or we could do a proper odor investigation to see where that smell comes from. So the next step would be to measure for temperature and relative humidity. If the relative humidity is very high in space, we have seen that it can favor the growth of bacteria and mold. So if we physically found mold in some areas and we found complaints and there are sick people that are showing symptoms of exposure to mold, then we could do a biological sampling in accordance with CIPSIS TM26, and we could find the sources of mold and clean them, and then do a proper investigation as to why that area is so wet, because, for example, we could have a leak from the roof that needs to be repaired. The next step would be to check the filters of the air handling unit, the supply and extract grills that work in accordance with EN 15780. And we could measure particles such as PM2.5 and PM10 and nitrous oxides. And if they are too high, or we live in a highly contaminated area, we could investigate the possibility of installing higher class filters. And finally, we have to consider the local aspects of the building. So, as Safi has mentioned, if we live in a high traffic area, it would be wise to measure for particles and nitrous oxides. If we live on a radon area, we could measure for radon and establish the corrective measures. And if we are working in a specific industry where we are exposed to certain chemicals or dust, we know that we must comply with the HSE regulations, and we know where to find the limits of exposure, and we can investigate that. And if we consider things like boiler rooms, or, for example, the fact that we are storing gas bottles in a space, we will have to investigate where we are storing and perhaps have alarms or tests for those contaminants to ensure the safety of the occupants of that space. Finally, to summarize this presentation, we have seen what good indoor air quality is. We have seen the definition of it and what requirements we need to have in order to have good indoor air quality. We've also seen what the main contaminants are, which are odors, gases, particles, volatile organic compounds, and bacteriological contaminants. And we have seen that the role of ventilation and maintenance is sometimes more important than anything else in order to have good indoor air quality inside a building. That's the end of the presentation. Thank you very much for attending this webinar. And if you have any questions, please feel free to email me at any time.